Dear students, welcome back to the online course of Ecological Modeling. After formulating the model equations last week, we will now continue with finding their solutions. Models are formulated by differential equations. These denote the rate of change of a variable in function of time. For instance, changes in c over time are driven by import and export processes of the system. They are just a function of time, c itself, and a set of parameters. We may be interested in two types of model solutions. First, we might want to find how c changes over a specific time. We refer to these solutions as a dynamic or transient solution. Or we want to find a solution at which changes are zero. Hence, where the system is in equilibrium, we refer to such a solution as a steady-state solution or an equilibrium solution. To find transient solutions, we essentially want to plot how the variable is changing in time. We do this by integrating the differential equation over the time period of interest. This can only be done when the starting conditions are defined. The initial conditions are thus essential to run the integration. We need to start from something to end with something. For instance, as you see for this model, which is by the way a formulation of a population growth model with density dependence, or the Lotka-Volterra population growth model, different starting conditions of the initial population size n0 lead to different trajectories of the population size in time. And as you see, these appear to converge to the same value over longer time intervals. For a population model, this is referred to as the carrying capacity, but in general, same model here with different initial conditions lead to different time courses. The carrying capacity is referred to as a steady-state solution, the solution for the equation which is independent of the initial conditions. So, for the same model, different initial conditions give the same ultimate value over sufficient long times. Analytical solutions are, because of their general description, mathematically most elegant, as the solution will be represented by a formula. It is always correct, so not subject to any error. The downside of this elegance is that they can only be found for simple models. Solutions for more complex models need to be found by numerical methods. Such methods give an approximate solution and are obtained by a computational algorithm for a limited number of points. R or other numerical software can do this for you. Let us first give some examples for getting transient solutions by integration, thus. Consider a constant rate change, here represented by A, so the differential equation becomes delta C on delta T equals A. If we start with a concentration B, the starting condition, then integration gives us for C at any time t the linear combination of the starting conditions plus the number of time steps considered times the constant rate A. Put alternatively, we start with a concentration B and simply add A every time step. The equation B plus A times t is thus an analytical solution which holds always for any t and is always correct. Now, what happens with a first order change? So, when a rate of change is proportional to the concentration C by a factor A. The differential equation is then delta C on delta T equals C times A, and again starting from a concentration B, we integrate and now find by basic calculus the analytical solution C for the moment t equals B times e to the power A times t. Or translated, the concentration exponentially increases in time. For some complex models, transient solutions can be found analytically as well, but you will need some solid maths which you will find in mathematical handbooks. So for instance, consider this example where C, concentrations in the lake, are determined by inflow and outflow, but also consumption processes. Concentration changes in the lake are the difference between what comes in from the river upstream but dilutes in the lake and what goes out, for instance by consumption. We here for simplicity neglect outflow by the downstream river. Starting from the initial conditions C0, the concentration at every moment t can then be analyzed using this equation as derived by calculus. You can imagine that finding such a solution needs well-developed mathematical skills, and even when you have them, it is possible that the analytical solution cannot be found. One way to overcome this issue is simply by using numerical integration, so by systematically adding the calculated difference to the conditions at the previous time step. When we take the time difference between steps infinitively small, the limit of the difference between the concentrations at t plus delta t and the concentration at t divided by delta t approaches the initially developed rate change. So we can simply calculate C at the time t plus delta as a sum of the concentration at time t plus the rate change times delta t. The good thing is that we can rely on computers for making these calculations. These integrators simply divide the time span in the number of time classes of relevant delta t, replace the derivative by the finite differences for a time step, and update C from previous time steps. The integrator used by R is the ODE function. Now, the steady-state solutions. Remember, these are the solutions for when the rate of change is zero, so when the system is not changing anymore or is in equilibrium. As earlier, we may find solutions by analytical or numerical methods based on root finding. Finding roots analytically is quite straightforward. Going back to the most complex model we saw, the river model, we simply need to equalize the rate expressions to zero and find the solutions for C. We refer to these equilibrium conditions as C star here. Putting all the terms with C on the right hand and those without on the left hand, simple algebra then brings us to the equilibrium conditions D divided by K plus D times C in. This solution is correct for any set of parameters D, K and the starting conditions C in. Again, easier is to use computational algorithms to find the roots. But in contrast to the analytical solution, this solution only holds for a specific set of parameters and constants. In R, we use a uniroot function for this. When we compare the analytical with the numerical solution, we see that some numerical errors always exist when steady states are simulated rather than analytically tracked. This is inherent to the procedure, as a numerical approach is only an approximation. All at all, we use R to solve these differential equations. We implement our code in scripts and in Markdown documents. Always provide a header with the content of the simulation and the authors. We define the model components, being the state variables and the parameters, and we use a hashtag to document the units. We define the derivative function and the model equations where we separate the rate expression and balance statements. Finally, we retrieve the solution by specifying the time interval and the duration of the simulation and calling the function in R to get the solution. Plotting is easy and straightforward. As explained earlier, the Transient solution is found by numerical integration, where we provide a function that gets as input the time value t, the values of the state variables at this time step c, and the parameters params. You must specify the derivatives of the state variables here dc. The ODE solver performs a sequential procedure. It calls this function multiple times and updates to the new values of the state variable. While many packages exist for solving differential equations, we are faithful to using R, as they are open source. While many packages exist for solving differential equations, we are faithful to using R, as it is open source and created by a community of scientists. You don't have to pay for the use of the software, but instead what is asked is to simply acknowledge the authors for their work. And we do this in science by citing their work properly in our publications.